Okay, hello again, Stillfish. We're going to talk a little about some big ideas related to the difference between factor analysis and principal components analysis. For those of you who have taken a chemistry class, PCA in chemistry is the exact same thing as PCA in statistics. Right, you're using like chemicals and shit, but it's the same idea. For those of you who have no idea what I'm talking about, that's okay. I'm not going to test you on chemistry because that's not this kind of class. All right, so factor analysis versus PCA. Factor analysis produces factors, while PCA produces components. This is a very subtle distinction, but factors cause item responses versus components, which are just aggregate, kind of like summaries of responses. I have a diagram to kind of illustrate this with arrows. So for our factor analytic model, the arrows go from the factor to the items. So you can see that with the arrows here, because what is happening is the latent factor is causing the responses on the questions. It's not like the questions are causing someone to become more conscientious. No. What's happening is someone who is higher on a latent factor of conscientiousness is making different choices and different responses. And we are using those responses and choices to infer what that individual's latent trait is. Right? Cool. Versus principal components analysis, which is a data reduction technique where the arrows go from the questions to the latent component. There is no theory here. There's not this idea that whatever that component is causing responses. No. It is a data simplification technique as a way to simplify your big giant data matrix into the smallest number of pieces that capture the bulk of variability. There doesn't need to be any overarching theme or logic. If the items move together, are highly correlated, then you can capture that movement as a component. But then again, just to iterate, the component does not cause the item responses. They are just a way to describe them. All right, so factor analysis analyzes only the variance among the variables. So that common variance without unique variance, versus PCA, which analyzes all the variance. Its goal is to summarize as much as possible. It doesn't care if they are theoretically unrelated but happen to be like associated. It'll exploit that association to give you the fewest number of components. All right. So factor analysis. Here's the kind of question it's trying to answer. What are the underlying processes that can produce these correlations? It's more theory driven is what I'm trying to get at. PCA is just a summary. It is super data driven. I love it. It does great things, but there's no theory. There's no divining from it. It is just how can we reduce our data into the smallest amount of chunks so we can save space on our hard drive. Right. So PCA begins with ones on the diagonal of our correlation matrix. Then it extracts as much variance as possible. And each variable is given equal weight initially in our pattern matrix. And then commonalities are estimated as the output of the model. These are typically inflated because, again, PCA does not care why things are related. It just wants to suck up as much variance as possible. So it will absorb method variance, anything that causes these items to move together. And that's what I mean by inflated. So this often leads to an over-extraction of factors. Again, not a fan of factor extraction, but that is a personal opinion that is not shared by everybody. But the reason it over-extracts is because it grabs more than just what is theoretically related to it. It grabs method variance, anything that these items have in common. Anything at all. Right. Factor analysis begins from a different approach, where its goal is to try and find the common variance. And this is done by estimating the commonality. So remember that SMC, and then placing it on the diagonal of the correlation matrix. So the diagonals are not 1, like they are for PCA. And then it analyzes only the common variance, only the stuff that all the items have in common. And its outputs typically are more realistic and smaller for their commonality estimate. And usually this results in far fewer factors. Now, selecting the number of factors is more of an art than a science, but I'm also a little biased here because typically fewer factors is better. All right, so what else? What are other key big ideas? How many factors do you extract? How many should you expect? And those kinds of things. So one convention is to extract all the factors that have eigenvalues greater than 1. Okay, this is the Kaiser criteria, and it's well-meaning, but it is very data dependent because in our data, an eigenvalue is weighted as a function of how much variance explains. So eigenvalues above 1 explain more than average, while eigenvalues below 1 explain less than average. So it's kind of artificial. Right. So another way is to extract all the factors with non-negative eigenvalues. This also has problems because essentially it is telling you to grab everything that has anything at all that can be moved together. It's a little over, so we can be used kind of like a, there are techniques is what I'm trying to say here. Another one, and this is kind of the classic old school technique, is to look at a scree plot. And I've got one on the next page. And this is the first technique I used, and it is an effective early approach. All right. Okay, so it's on 2 slides, so I'll show you it in a bit. But another approach is to try and extract multiple factor structures and see which gives the best interpretation, which has the best fitting model, which is most closely aligned to theory, and compare them. All right, so here's a table that illustrates eigenvalues. And we can see that as the eigenvalues increase or decrease, we explain more and more variance. Here's some lovely SPSS output, essentially. So I encourage you to crawl in, just take a look, and enjoy. Scree plot. All right, so here's the scree plot. And the early advice I was given was look for the elbow. What does that mean? Okay, let's back up. So a scree plot is plotting the eigenvalues in relation to the number of factors. So, and these are deliberately ordered from highest eigenvalue to lowest eigenvalue. And when we look at the plot, the anecdote is find the elbow. And what that elbow is where's kind of the law of diminishing returns. Where do the eigenvalues stop really adding meaningful contributions? So here, I would argue that the elbow is probably at factor 4, but I could also see totally plausibly it stopping at factor 3. Because every factor after that has just tiny little diminishing returns in eigenvalues. There are problems with this technique, obviously, but this is kind of the way to think about it. This is probably the easiest technique to use. Okay, so what else? What other things? So how do you know when a factor structure is good? Um, Frankly, when it makes sense and is pretty simple. Uh, and that is typically when it is the most useful. Now, how do you interpret factors? That is a good question where the true art of this technique comes in. I am terrible at, at in giving factors nice names uh, because, well, frankly, I'm really impatient, and what I tend to do, and this is an approach, is I pick whatever the highest item is, so the item that is most closely related to the factor, and decide that that is the name of the factor. Uh, um, is it a great technique? No, but it's consistent. So yeah, cool. Okay, so that is wrapping up a very rapid crash course in factor analysis. Um, yeah. Uh, Next week I probably won't be a fish. Thanks for hanging in there. I apologize that this probably felt a little mathy, which either you loved or hated, and I'm very aware of that. So I will see you all later. Thanks for hanging in there, and bye.